So let's have several discussion points here. So what we did is we made a field redefinition, which we are always allowed to do. Yep.
Isn't QB like a helicity eigenstate of positive helicity? And the other one
We're talking about heavy particles, so helicity is not such a good thing.
I know, but it's like a 1 plus p.
Yeah, I'm going to talk more about it in a second. Yeah. Yeah, give me a minute. And then if you still have a question after I talk about it, then ask. So first of all, what we did here was tree level. Okay, so when we make this type of redefinition and we go through this algebra, it's all tree level. Not thinking about any loops here. There will be corrections to this story once we start talking about loops, and there will be corrections to this story, namely that we just get the same LHQET once we want to take into account one of our M corrections, and we'll come back to both of those points. So both of those things to be discussed later. What we do with LHQET is we describe correctly the couplings to gluons at leading order. And often what people are interested in with K-mu here is K-mu of order lambda QCD, separating the scale lambda QCD that has to do with the confinement into a meson, like a B meson, from the scale of the heavy quark. Okay, so the antiparticles are being removed. This is point number 2. So if you want to ask what is it that we're integrating out in this theory, we're not integrating out the particle because we want to study it. We're integrating out the antiparticle. It's easiest to see that if you go to the rest frame. So taking V rest frame, which is just 1, 0, 0, 0, just time-like component, then our 1 plus V slash becomes a, so if we have 1 plus V slash, then that's just 1 plus gamma 0 over 2. And if you want to talk about particles and antiparticles, the best representation to use is the Dirac representation, because then the particles, so we'll take a spinner in the Dirac representation, could be part of a field, could just be a spinner for an external state. In the Dirac representation, what happens is that you have the guys that are the particles in the upper 2 components and the guys that are the antiparticles in the lower 2 components. So this is particles. This is antiparticles. This guy's always projecting onto, in the rest frame, into the particles and antiparticles. It's just that if you write it in other representations, you'd have more trouble seeing that than in the Dirac representation, where you just have a 0. Okay, so this is one way of thinking about why this what this projector is doing. It's getting rid of the antiparticles. So the way you should think about this physically is that if you're studying some process, you're studying heavy particles close to their mass shell. So what we're doing is we're measuring fluctuations near the heavy mass, MQ. We're perturbing about MQ. If you're perturbing about MQ, the antiparticles are very far away, because the splitting between the particles and the antiparticles is 2MQ. So that's why they get integrated out. So that's why in this language of being near MQ, the antiparticles are just very far away, and we don't want them in our theory. One way of talking about that is pair creation. So if we draw some type of time order perturbation theory diagram for pair creation, so it's not a Feynman diagram, but a TOPT diagram, just so we can talk about a definite intermediate state at a definite time. Then this intermediate state here has 3 heavy particles, and it has, if this guy has MQ and this guy has MQ, this guy has 3 MQ. So this intermediate state is off shell by 2MQ. This is a time-ordered perturbation theory diagram. So I can talk about whether something's definitely a particle or definitely an antiparticle. And another way of seeing this 2MQ that I'm talking about is like just to do vacuum polarization, where you have 2MQ. You need 2MQ of energy to fluctuate into a heavy quark pair. So if you have a very light gluon, then it just doesn't have the energy to do that. So pair creation is not part of this theory. Okay. So now you can ask your question if there's still a question. Yeah. All right, so the thing we're getting rid of is the antiparticle. Now, because we're getting rid of the antiparticle, we no longer have an annihilation process. So unlike QCD, where we can have particles and antiparticles annihilate, here we have actually a conservation rule for the number of heavy particles. So if we're talking here about quarks, the number of heavy quarks is preserved. And that's an extra symmetry that this theory has. That QCD didn't have. Okay, so the conservation law for the number of heavy quarks is a U1. More generally, we can extend this to something called heavy quark symmetry. So since we notice that there's this conservation law, let's think about what the biggest group we can come up with is. It describes the symmetry of this LHQET. So this U1 that preserves the heavy quarks is a flavor symmetry. And depending on how many heavy particles we have, it could be bigger than a U1. So actually, it's a UNH for NH heavy quarks. So you could have some heavy sources that live under some group. And if you have N types of those sources, you'd have a UN symmetry. And the root of this is that we got rid of MQ. MQ is the thing that would break this symmetry, but it disappeared. And once it's gone, we don't care. We don't know whether the thing that was a charm quark, or a B quark, or a top quark. We don't see the flavor of the quark anymore, because the mass term was what was tracking that flavor, and now it's gone, and we just end up with this theory that doesn't remember about the flavor, so we have a flavor symmetry. Okay, so that's kind of cool. It's an example of having an effective theory where there's an emergent symmetry that wasn't so apparent in the theory you started with, but is apparent once you get to the effective theory. The other example is spin symmetry. There's actually an SU2 spin symmetry because the Lagrangian didn't involve any d slashes anymore. It just became a scalar, the v dot d. So if we think about our heavy particle, so we think about a 4-component spinner. 2 degrees of freedom have to do with particle versus antiparticle. The other 2 have to do with spin, a half. And we don't care about the spin either because our Lagrangian is completely scalar. Okay, we just had QV, I v dot d, QV, and there was no, we didn't mention, the v dot d doesn't have any d slash, it doesn't have any spin matrices in it. Okay, so that's an SU2 symmetry. So if we want to talk about that, again, it's useful to think about it in the rest frame. In the rest frame, the heavy quark spin transformation in some Dirac representation, which is gamma 5, gamma 0, gamma I, is just the Pauli matrices, sigma I. And you could think of making a transformation related to this spin. So the infinitesimal version of that transformation would look like this. Start with QV, do a rotation, ask, does this change the Lagrangian? And the statement is that the change to the Lagrangian that you get is just I v dot d commutator I epsilon dot SQ. But I v dot d is just a scalar quantity and just commutes through this epsilon dot SQ. Okay, so that's the formal statement that there's a spin symmetry. Since we're using this kind of projected formalism, you can ask the question, well, maybe this spin symmetry is mixing up the heavy quark components that, with the other components, that these 0 components, but you can check that it doesn't. It's actually acting within the subcategory, which is just describing the heavy quark. So you can also check that. One way of phrasing that is that you can check that this is true, so that the rotated field still satisfies the projection relation. So it's really, this is a rotation that's within the 2-component subspace that are describing the physical degrees of freedom. Okay, so there's this enhanced symmetry group of this theory. And we can put it together because nothing stops us from doing this and doing this or doing a bit of both. So we can build one big group. So altogether, you have a U, 2, and H. And that's heavy quark symmetry. QV field is a fundamental in that group. So you talk of spinners that look like this with some number of components, and this guy could be, for example, maybe this is a B quark with spin up, and then some other component might be a charm quark with spin up or a B quark with spin down. That's what heavy quark symmetry is. Okay, so any questions about that? So we'll talk a bit more about how you actually make predictions related to this heavy quark symmetry. As you saw, it's kind of emergent, and so we should build some tools for seeing what kind of impact that has on observables, and we'll spend a little bit of time doing that today. Before we do that, let's continue our list. So when we made this field redefinition, we pulled out this phase. That phase depended on V, and we also stuck a label V on the field. So we had this V mu, which appeared on our field. Okay, and that was just a reminder that we pulled out a phase, and the phase depended on our choice of V, and we could make actually different choices. This V mu is actually something quite useful because it isn't changed when you talk about low energy QCD interactions. So it's a conserved quantity. So in our notation of dividing up P into MQV plus K, this changes. So if you tickle with with very soft gluons, the heavy quark, you can't change this term, but you can change that term. So the V term is not affected by the gluon interactions. It's a conserved quantity, and hence having it as a label on our field tells us what V we're talking about. Basically, what V signifies is you could talk about a heavy quark in its rest frame, and then you could talk about tickling it. Or it could be moving with some constant velocity, and you could talk about in that moving frame tickling it. And any such choice is equally valid, and that's what V is encoding. Okay? But we can formulate tickling a heavy quark in any given frame that we'd like, and V is encoding that. Things are kind of natural to see in the rest frame, but we don't have to work in the rest frame, and that's what V is encoding. Okay, so that's kind of different than we've seen before. What's the power counting? Power counting is not so difficult here. It's just power is 1 over mq. So our leading order Lagrangian had no mq's. And then we could formulate corrections to that leading order, and they would be suppressed by powers of 1 over mq. So let's think about that in a little more detail. So if you take the field Q of x and you write out the mode expansion for the field, so there's this term, and then there's a term. Involves the antiparticles. What we did with the Q of x field, that's the full theory field, is we pulled out this phase. And the phase that we pulled out was just something that depended on a fixed quantity, mv. So it would come outside that integral. So we pulled out so you can think about really literally sticking P into this formula and then pulling out that phase. And then that leaves in QV just the e to the minus I k dot x. Okay? So if you think about derivatives on QV of x, then they are scaling like k. And this guy here has no mq's in it. So there's no mq's in the derivatives. So if we build operators out of this QV field, and we let derivatives act on that field, there's no factors of the heavy quark mass hiding anywhere in those derivatives. That's the magic of making this kind of phase redefinition. That we've made the MQs explicit by pulling that out so that we could get something remaining that doesn't have any MQs. since we want to count MQs, what we want to do is we want to make all the MQs very, very explicit. We don't want any to be hiding anywhere. And that's what we were doing before with this field redefinition, was making all the MQs explicit. This is one example of why that's important.
This means you have to restrict to small gauge transformations, right?
Yeah. So you should, well, if you think about the action, if you think about the action and you thought about making a gauge transformation, you could worry about making a gauge transformation that would inject too much momentum into your field, so that it no longer described low energy degrees of freedom. But usually people don't talk about that so much in HQET, so we'll save that discussion for SCT, where we will have it. So the coordinate x, one way of thinking about this equation is that the coordinate x that's in QV really corresponds to variations that are the low energy variations. So our field is doing what we want. It's describing low energy fluctuations. And that's another way of thinking about what this, the fact that there's no MQs in this derivative. So if we look at subleading operators, and if we look at subleading Lagrangians and external operators, all the powers of MQ are going to be explicit, and that makes doing the power counting quite simple because we just look at them and count. So as long as we're sure that they're all explicit and none are hiding anywhere, then it's easy to count. There will be logs of MQ hiding in Wilson coefficients, but we're not counting logs. If we're just counting powers, then what I said is sufficient. OK, so is there any questions about that? So there's actually one MQ that's hiding, and we should be a little bit careful about it. So if we talk about states, there's actually an MQ hiding in there. So let's think about states of some particle that's relativistically normalized. It could be a heavy meson. Let me just call it H. And the usual normalization convention for a relativistic particle is this one. For the states. So this guy, if you look at the dimensions of the right-hand side here, you've got -3 plus 1 is -2. So each of these is dimension -1. So that's one thing we can track. But if you think about what this EP is, this EP has the M still hiding in it. So this EP is really the physical on-shell energy, so it's mq squared. If this was a heavy hadron, for example, it'd be mh squared plus the 3 momentum squared. And mh for a heavy hadron has an mq hiding in it. OK, so what we have to do if we want to make everything explicit is use HQET states. And you can think of HQET states simply as the states that you get if you define your quantum field theory using LHQET. So this is the MQ goes to infinity, so it's just the leading order term. And if you define your states with this Lagrangian, you can still talk about a bound state like the B meson, because the B quark didn't go away, it just became static. And all the dynamics of the light degrees of freedom that are making it into a hadron are still there, and they're described by a usual QCD Lagrangian. So you still have hadrons, so you still have a B meson, but it's not the same because you don't have any MQs. They're all gone. So you can't possibly have this formula for the HQET definition of the state. And so the way that you should think about this is that the relativistic version of the state is related to the HQET definition by a formula like this. So the HQET definition is this HV, the relativistics is this HP, and there's some normalization factor between them, and as well as there can be 1/m type corrections. Actually, both things are there. And if we talk about this HV field, where V is some external label telling us the velocity, and K is describing some residual momentum of that field, of that state, the normalization convention would be as follows for HQET. So I've still left it to be 2. Sometimes people remove this 2 as well. But so there's several things going on here. One is that V and V prime, in order for these states to have overlap, we're saying that you should be talking about hadrons that are moving with the same velocity. Remember, velocity is conserved. So if we had 2 things in different sectors, they just wouldn't overlap. That's this Kroneckov delta. This delta 3 of K minus K prime is exactly the analog of this guy over here, but now it's with the K, which is the residual, has no MQs. And I got rid of the MQ. I got rid of the thing in the numerator. That was pulling out this root MH. So there's no MQs in that formula, and that's the right way of thinking. So you have to remember, if you have some formula for the cross-section that you derived with relativistic states, which all of the formulas you're used to are derived that way, you have to remember about that root MH when you're going to make predictions with the HQET. And the same thing actually is true of the spinors. There's a square root of the quark mass hiding in spinors, and you have to take care of that as well. I think I'll leave that for your reading. OK, so up to these little subtleties here, that's all the MQs that you have to keep track of. And once we've kept track of all those MQs, then we know how to do the power counting in this theory.